Good evening. Today we are going to discuss the image charge method. As you will see, the image charge method is both science and an art, and we'll talk about it. But the first thing that makes this image charge method possible is the uniqueness theorem. The uniqueness theorem is very, very important. So if you haven't understood it completely, I suggest that you watch from lectures 15 to 17, mainly lecture 15, where we talk about the uniqueness theorem in greater detail. So essentially what it says is that if you have, our goal is to find some scalar function phi of r theta phi or x, y, z. Our goal is to find a potential that satisfies the boundary condition so we can find the electric field. And the uniqueness theorem tells us that as long as the scalar function phi is satisfying the boundary conditions properly, then it is the unique solution to the problem. And that's what we're going to take advantage of in the image charge method. So to talk about the image charge method, we will start with an example. Assume that you have an infinite conducting plane in xy plane. So you have an infinite conducting plane that I'm drawing in green here. That's in the xy plane, so it's extended this way, right? And then we have a charge. We have a charge plus q up here, and this is at a distance d about the z-axis. So this point would be z equal to 0. And what we have to do is find out the potential for this problem. And this infinite conducting plane is grounded. So if this infinite plane is grounded, then that means phi is equal to 0 on the surface of the plane here because it is grounded. So we have our first boundary condition there, that phi at z equal to 0 is equal to 0. And the second boundary condition is obviously phi should go to 0 as r, in this case square root of x squared plus y squared plus z squared, is much greater than d, right? So if you are far away from the charge, the potential should go down to 0. So these two would be our boundary conditions for the problem. So now here in this problem, we cannot say that potential is simply just kq by r. This is not the answer, because the presence of this charge would mean some negative charges would be induced on the conducting plane, and so the overall potential is not just kq by r. So then how do we solve this problem? So to do this, we're going to take the advantage of uniqueness theorem. So our goal is just to find some scalar function phi that will, in this case, we want to find a scalar function for the potential, that is phi of x, y, z in this case, if we are using rectangular coordinates. And our boundary conditions are phi goes to 0 at g is equal to 0, and it goes to 0 as you go away to infinity. And this comes because our plate is grounded, right? So we are going to find the scalar function phi here by using a different configuration. It doesn't matter if you use a different configuration as long as we are able to satisfy the boundary condition. The uniqueness theorem assures us that our solution would be unique as long as we satisfy the boundary condition. So what we are going to do is we are going to substitute this infinite plane problem with something else. So here we have q at a distance d, and this is x, y, z. So instead of this, we'll consider an alternate configuration. So here I have plus q at a distance d above, and I have minus q at distance d below. This is XYZ. So this is an alternative configuration that I'm considering, and I'll show you in a minute what we are doing here in a more general sense, but for a moment consider this configuration. So if you want to write the total potential in this case, f of phi of xyz, then you have the potential from the positive charge plus potential from the negative charge. Potential from the positive charge should be k times q by, if you are, say, at some point here, at some point p, right? So then your denominator would be x squared plus y squared, and notice that the charge is d above the z axis, so the z coordinate will have z minus d squared. That would be the distance from the charge to the point if the point is labeled as xyz in 3 dimensions, right? So then similarly for the negative charge, it would be very similar, except you have a negative sign, and kq divided by square root of x squared plus y squared plus z plus d whole square, right? And z plus d because it's minus d when you're going down, so it's minus of minus d gives you a plus, right? So wherever this is, you have to first go from a depth d all the way to 0, and then you can go to the point P. So now if you take a look at this potential, I can take kq as common, and I would have 1 over square root under x squared plus y squared z minus d squared minus 1 over square root of x squared plus y squared plus z plus d whole square. So this would be the potential for this problem. Again, what we are trying to do is we are trying to originally solve this original problem of an infinite plane that is grounded and you have a charge q at a distance d above. But because of the uniqueness theorem, now we set out to find some scalar function phi of xyz that satisfies the two boundary conditions for the original problem that we identified. And the first boundary condition there was phi at z is equal to 0 is 0. That is because the plate is grounded. So because the plate is grounded and the plate is positioned at z is equal to 0 for the entire xy plane at z is equal to 0, the potential is 0. Now let's look at this function that we got for the alternative problem. Let's see what is the value of phi xy and z is equal to 0. If you look at that, you have kq. So if you set z is equal to 0, this would be 0, this would be 0. You have a minus d squared term here and a plus d squared term here. So because it is squared, it doesn't matter, and you get essentially x squared plus y squared plus d squared minus the same thing, x squared plus y squared plus d squared. And naturally these two cancel out and give you 0. So it appears that this alternative situation, this alternative configuration seems to satisfy the first boundary condition. Now if you look at the second boundary condition, you have two potential terms in the alternative configuration, one coming from the positive charge and another coming from the negative charge, and both of them have r in the denominator. This is just simply kq by r. So as you go to infinity, each term goes to 0. So phi would go to 0 as r goes to infinity. So this scalar function satisfies both the conditions. Then from uniqueness theorem, we know that this must be the solution, right? So then we can write the solution for our original problem as kq 1 over square root under x squared plus y squared plus z minus d whole square minus 1 over x squared plus y squared z plus d whole square. So this potential satisfies, this scalar function satisfies the boundary condition that phi at 0, z is equal to 0 is 0, and phi goes to 0 as r goes to infinity, which are the boundary conditions that we have for our original problem, where we have a conducting plane that is being grounded. That's the first condition, and there is a charge here up here, and this is a generalized boundary condition. So this satisfies both the boundary conditions for our problem, So this must be the solution from our uniqueness theorem. So let's now having seen briefly what it is, let's try to digest the image charge method a little more. So what did we do? We had our original problem is that we have a plane and we had a charge here. So we placed an imaginary image charge, and we are calling this image because this plus q is a distance d above, and in our alternative configuration to find out the scalar function that satisfies the boundary condition, what we did was we placed another charge, some other charge q prime, at some distance x prime. And it just so happened that in the previous example, to satisfy phi z is equal to 0 is equal to 0, we call this minus q. So in general, in image charge method, what you do is you replace the situation that you have with an image charge that is placed at some distance. So finding out what this image charge is and what this distance is what is tricky. There is no direct method to that in a way like you would do with separation of variables, for example, right? So that's why I called it a little bit of an art and a science. So in the case of the in the case of an infinite plate that was grounded, that is the first problem. It was pretty straightforward, and we could find that imaginary charge very easily. So the imaginary charge was, we said, if there is a plus q above a plane here, this problem is equivalent from the view of boundary conditions to plus q and minus q. So when we say equivalent here, you have to note one thing, that the potential would be equal, the electric field would be equal, but the energy density would be half, because in reality you don't have two charges. In reality you have only one charge. Here in the equivalent situation you have two charges, and so the energy is half for this system because there is only one charge here. So you are trying to solve this system, and you are replacing this system with an image charge system so that you can more easily find. So if we do another example, I think it'll become more clear. So let's do another example. Instead of an infinite plane, let's now consider a sphere. So we have here a sphere, and the sphere has a radius of r, and there is a charge q at a distance s from the sphere, and the sphere, let's say, is grounded. So we have phi is equal to 0 on the surface of the sphere, and now we are asked to figure out the potential. So this is very easy to do with separation of variables. So in fact, I would encourage you to see how you could do this with separation of variables. All right. So you would start with the general solution from L is equal to 0 to infinity AL RL plus BL by RL plus 1 PL cosine theta. So you would start with that and then figure out the answer. But if we want to do this with image charge, that means I have to place some image charge inside the sphere, right? So I'm going to place some image charge at a distance a. I'm going to place some charge q prime here. This is an imaginary image charge, so this is an imaginary image charge. And the reason we are placing this imaginary image charge is because we want to essentially figure out phi of r theta phi that satisfies the boundary condition, right? Phi is equal to 0 on the surface, and phi goes to 0 as r goes to infinity, right? That's all we want to figure out. So to do that, we're replacing the physical situation we have. The physical situation we have is plus q is outside a sphere, but we are placing this imaginary charge. We are only placing it in our mental frame, in our mental construct. It's not really there, and we are doing that to find the scalar function more easily. So then our situation, our image charge situation would look like I have the center of the origin of the sphere, and then at a distance a I have q prime, and at a distance s I have plus q, right? And this is what is, if I am interested in finding out what is the potential at this point, at point P, right? From origin to that point P is the vector r, right? And I can connect this, and I can connect this as well. And then I'm going to call this angle theta. That is the angle at which the point P that we are interested in is. And then now if I try to look at, phi of r theta phi, then it's very simple. I have kq from this divided by r minus s along z, if we call this as the z-axis, right? And then similarly I have kq prime divided by r minus az, right? We are trying to figure out the potential at point P, and we are labeling the charge as q prime and the distance as a, because unlike the previous example where we knew that I have to place negative q at a distance d below, so here we had the image charge to be negative q and we placed it at a distance d below. That we just did it, we just said let's do this, right? There is no, it's not an algorithmic process. That's why I called it a little bit of art there, right? So here we're trying to do it a little more methodologically, and so we said let us place some charge q prime. We don't know what the amount of the charge is, and we're going to figure that out. And the way we are going to figure that out is, we know that we want our boundary condition phi at r is equal to r, theta phi is equal to 0. We want this scalar function to satisfy this boundary condition. So we can rewrite this potential again. So I'm going to draw the picture again. I have the origin. I'm looking at the potential at point P, and this is the z-axis, and the point P is at an angle theta. My original charge is here, that is plus q, and this distance is s, and the image charge I'm placing here, q prime, and this I'm calling a. So I can connect this. I can also connect to this. So you can use a law of cosines and rewrite the potential. The potential that we got for this configuration was k times q by r minus sz for the first charge, and for the second charge kq prime by r minus az. So from the law of cosines I can write this r minus sz, the magnitude of that is essentially r squared plus s squared minus 2sr cosine theta. It's law of cosines, right? So this is r here. So if I take this triangle, let me draw it in a different color. So if I take this triangle, the triangle between origin, point P, and charge Q, if I take this triangle, this angle is theta, this is r, and this is s. So I can get this side from the law of cosines, and this would be equal to square root of r squared plus s squared minus 2sr cosine theta, because this is not a right angle triangle, right? So similarly, I would have plus kq prime. For this one, I would be considering the triangle. For this one, I would be considering the triangle, this triangle. I would be considering the triangle OP and Q prime, and that gives me square root of r squared plus a squared minus 2ar cosine theta, right? So then our boundary condition is that phi at r is equal to r, theta phi is equal to 0, because we grounded the sphere. So the sphere is grounded, so phi is 0 on the surface. So that's what is this boundary condition that I'm rewriting on the next slide, right? So from this function, I can see that phi at r is equal to r would be kq by square root of r squared plus s squared minus 2rs cosine theta plus kq prime divided by square root of r squared plus a squared minus 2ar cosine theta, right? So now somehow this is kq prime. Somehow we want these two terms to cancel out and give us 0 to satisfy this boundary condition. And to do that, first let's look at this denominator here. We're going to take this term. I'm labeling a star. So if I look at the term that I labeled as star, it looks like r squared plus a squared minus 2ar cosine theta, right? So I want to make this term look something like this, right? So to do that, what I'm going to do is multiply and divide, right, with a by s, because I want the cosine theta terms to look similar, because what I'm trying to get at is I'm trying to pick a charge q prime and a distance a such that these two terms will cancel out, satisfying the boundary condition. That's the art part of it. The art part of it is that how do you pick an image charge q prime, and how do you know the distance that you have to place it at to figure out a scalar function that satisfies the boundary conditions. So we started with, well, we don't know what should be the amount of the image charge, so we're just calling it q prime, and we don't know where to place it, so we're calling it a, and then we're punching in the numbers, and somehow we want these two terms to cancel out, the first term and the second term to cancel out to give us 0, particularly at r is equal to r. So we plugged in r is equal to r, and now we're looking at the second term. So we're going to multiply and divide by a by s, or pull out a by s as a common factor. Then I would get s by a r square plus s by a times a square minus 2ar s by a cosine theta, right? So that would give me a by s by a r square plus sa minus 2rs cosine theta. So you can see that we got the cosine theta term. We changed the cosine theta term by pulling out a by s, right? Now we can suppose then that we can choose a, because it is up to us to choose this a, right? So we can choose this a. That's up to us. So if we pull out a by s, you get s by a r square plus sa minus 2 sr cosine theta, right? So if we are going to choose this a such that it is equal to I don't know why it is disappearing. I apologize for that. So let me write it on the next slide. So we had r squared plus a squared minus 2ar cosine theta, and we change this to a by s by a r squared plus sa minus 2sr cosine theta by pulling out this as as a common factor, and it is up to us to choose this a, and so a, we are choosing it as r squared by s. If I choose a as r squared by s, then I would get a by s by, or this implies that s by a would be 1 over r squared. Sorry, so we would have this. Sorry, this would give us. Let me erase this. So we have a is equal to r squared by s. So s by a would give us s by r squared times s. So it would give us s squared by r squared, right? So we get S squared by R squared instead of S by A here, and R squared plus, and SA is equal to R squared. So then this is equal to R squared minus, this is just 2SR cosine theta. Then this R squared and R squared get cancelled, so I would have A by S squared plus R squared minus 2SR cosine theta. So if we go back to our potential, the potential that we wrote with the image charge came out to be KQ by square root under R squared plus S squared minus 2SR cosine theta plus KQ prime by square root of R squared plus S squared minus 2SA cosine theta. We took this term, we started with this term, we called it the star, and then we massaged it a little bit to get this SR cosine theta term first, and then our goal was to make this look like this, right? And to do that, we suppose that A is equal to R squared by S, because the distance at which the image charge is placed, we are placing this image charge in our mind to make sure that we get a scalar function that satisfies the boundary condition. That's what the image charge is about, right? So we can pick and choose this distance. This is not a physical real thing. There is no real Q prime charge there. We're just placing it in our imagination to solve the problem. So we can pick and choose the distance we place it, and we pick that distance as R squared by S just so that we would get this form, right? So then if I were to plug this form in there, right, S by A is S squared by R squared, so A by S is going to be R squared by S squared. So if I plug this in there, this is going to give me R squared by S squared plus S squared plus R squared minus 2SR cosine theta. So then I would get KQ by R squared plus S squared minus 2SR cosine theta. We did nothing with the first term. We're only manipulating the second term because that's the image charge we placed. KQ prime, and under square root I have R squared by S squared plus R squared minus 2SR cosine theta. Now we can clearly see that I can pull this R squared by S squared out of the square root, then I would just get R by S, and then I can flip that into the numerator. So then I would get KQ by square root of R squared plus S squared minus 2SR cosine theta plus KQ prime times this R squared by S would flip over, so I would get S by R divided by square root of R squared plus S squared minus 2SR cosine theta. So that's our potential at R is equal to R. So this at R is equal to R, that's the potential we got. All that we did is we took the second term and changed it to make it look like the first term, because what we want is we want these two terms to cancel out and give us phi equal to 0 at R is equal to R, because that's our boundary condition. So in the image charge method, once again, in the image charge method, what we are trying to do is we are given a real situation. That real situation has boundary conditions, and we want to find a scalar function, scalar potential, that satisfies these boundary conditions. So we are coming up with an imaginary situation where the scalar potential is easier to find, and we can make that solution fit the boundary condition. You can pick any scalar function and make it fit the boundary conditions, and the way you make it fit, you can figure out what the image charge should be and where you should place it. And that's what we're doing here. We just started with the assumption that the image charge is Q prime and it is placed at a distance A, and by picking a particular distance, A equal to R squared by S, this R is the radius of the given sphere, and this S is where the positive charge plus Q, the real physical charge, is placed, right? And by doing that, by doing some mathematical manipulation there, we were able to get to this state. So we got phi is equal to, at R is equal to R theta phi, to be now KQ by square root of R squared plus S squared minus 2SR cosine theta plus KQ prime times S by R divided by the same denominator now, because that's what we did on the last slide. So if we want this to be 0, then Q must be equal to minus Q prime by SR, right? That means Q prime is equal to minus Q times R by S. So if you were to place an image charge that has a magnitude of minus Q R by S at a distance A, which is equal to R squared by S, then that image charge situation resembles the original situation because it satisfies the boundary condition. And as you can clearly see, because we have this term in the denominator, phi automatically goes to 0 as R goes to infinity. In other words, the way we solve the problem of this spherical with positive charge plus Q here, and we grounded this, so phi is equal to 0 here. The way we solve this is if this is at a distance S, and if the radius is R, then I am picking a distance A, which is R squared by S, right? And I'm placing a negative image charge, that is negative QR by S, and this situation will solve the problem. So then we can write in general phi of R theta would be equal to KQ by, the first term remains the same, that is R squared plus S squared minus 2SR cosine theta. So here we have R is equal to capital R because this is the boundary condition, and here we are writing in general. So plus the image charge is minus QR by S divided by the same thing, right? Divided by R square plus A square minus 2AR cosine theta. But we know that A square, instead of A square, we can write R to the power 4 by S square, right? We can write that. So we can write R to the power 4 by S square, and here we can write R squared by S. So now we have figured out what the solution should be, and that's what gives us the potential in the image charge. As you see, image charge method is, you need a lot of intuition to come up with a situation that resembles the problem you're looking at. So that's why image charge method, it comes with, it's as much art as it is science. So let's try to solve the same problem, right? We have a sphere and we have some plus Q, right? So we can solve the same problem with separation of variables, and that's what I'm going to show in homework 6. So I'm going to solve a problem that has a charge inside a sphere, so that you can see how you could solve this kind of a problem with separation of variables. So for that, this is on homework number 6, and I think it is problem number 2. So I'm going to solve that, and based on how I solve that, I would like you to solve this problem with separation of variables. So I'm not going to directly solve this problem because I solved it using the image charge method. I want you to solve it using separation of variables. So I'm going to show you another version of that same problem, but now the charge is inside, plus Q is inside the sphere, right? So then you can use the separation of variables. So in case of separation of variables, we have a generalized solution. Our generalized solution is phi of R theta phi is sigma L is equal to 0 to infinity AL R to the power L plus BL by R to the power L plus 1 PL of cosine theta, right? And we're setting M is equal to 0 here because we have spherical symmetry. So obviously inside we have a charge, so we cannot directly apply the Laplace equation, because Laplace equation for Laplace equation del square phi is equal to 0. So we're going to consider the situation of just the sphere plus the charge. So if you look at the potential inside, so inside of the potential, and then you have outside, and I think in the problem in homework 6, problem number 2, the surface potential is being maintained at phi 0 cosine theta, right? So if you look at phi inside, you have the potential from this charge kq by r plus you have this term, that's the generalized solution, but inside, as r goes to 0, if I have this term, then phi of r would go to infinity, right? So inside, I have to set BL inside is equal to 0. Otherwise, my potential would diverge. So I would have, in general, L is equal to 0 to infinity, AL r to the power L, PL of cosine theta. So similarly, if I look at phi outside would be sigma L is equal to 0 to infinity, right? So outside the sphere, r can go to infinity, and for that we need the boundary condition of phi going to 0, so we need this. So naturally outside, I'll have to set AL outside is equal to 0, otherwise this term can make the potential diverge. The first term, AL to the r to the power L, can make the potential diverge. So then I would have here BL out by RL plus 1 PL of cosine theta. And we are given the boundary condition that at r is equal to r, we have phi naught cosine theta. So at phi inside, at r is equal to r, should be equal to phi outside at r is equal to r, which should be equal to phi 0 cosine theta. This is our boundary condition. So now we have the expressions for phi in and phi out, and all that we need to do is plug them in here. So related to the previous problem, just like how I placed kq by r as an extra term here, if you're trying to solve this problem, you will have to modify phi out to have kq by some r minus. So you'll have to modify the potential r minus some s if this is at a distance s, right? So r minus sz. This is what the potential extra term, plus you would have something like L is equal to 0 to infinity BL by RL plus 1 PL cosine theta. So in this example, in problem number 2, we're adding the point charge to the inside potential, whereas for the outside potential, we're not adding anything because there is no charge outside. The charge is inside the sphere. So here in this problem, the one that we use for image charge, you would have to add this potential to the outside, not inside. So that's the only difference. So then you set the boundary condition phi naught cosine theta. In the previous example, this would just be 0, right? But if you do that, we have kq by r plus sigma L is equal to 0 to infinity AL, or this is kq at r is equal to r. So we are looking at phi inside at r is equal to r theta phi. So that is r to the power L PL cosine theta. And similarly outside we have sigma L is equal to 0 to infinity BL by r to the power L plus 1 PL of cosine theta, and this is equal to phi naught cosine theta. So now if I look at the Legendre polynomials PL of cosine theta, for L is equal to 0, P0 of cosine theta is simply 1. You can do this from the generating function for Legendre polynomials, which we have seen in previous lectures. And for L is equal to 1, P1 of cosine theta is cosine theta. And for L is equal to 2, P2 of cosine theta, you can figure that out, and that should come up to be half 3 times cosine squared theta minus 1, right? So if P1 cosine theta is cosine theta, then if I look at this term cosine theta, I can just call it P1 of cosine theta. So I have two equations where I have a series of terms here. series of terms which are being summed from L is equal to 0 to infinity. Same thing here, series of terms from L is equal to 0 to infinity. But on the right hand side, my boundary condition imposes that I have only P1 because I have phi 0 cosine theta. So if I have only P1 here, then because these Legendre polynomials are orthogonal, then we can see that from this series we need only L is equal to 1, for example, outside. Right. So if I just look at just these two terms, then if I look at L is equal to 1 term for this, I would get B1 by R square P1 of cosine theta is equal to phi 0 P1 of cosine theta. And P1 of cosine theta is cosine theta. Right. So these two cancel out. So for outside, B1 outside, this is all outside, right, and this is inside. So B1 outside is simply phi 0 times R squared. And inside is a little more than just L is equal to 1, because in addition to having the summation of L, we have an extra term KQ by R. This is coming from the point charge inside the sphere. Right? So we need to have, if I look at this part, I'm going to show it in red. If I look at this part, equating it to this part, I'm going to write that on the next slide. So I'm equating this part inside to the boundary condition. We got this by equating the potential outside to the boundary condition. So if I equate the potential inside, that is KQ by R, plus a series of terms going from L is equal to 0 to infinity, AL R to the power L, PL of cosine theta is equal to phi 0 times P1 of cosine theta. So it won't work out if we just pick L is equal to 1, because if I just pick L is equal to 1, then what I would get is A1 R P1 of cosine theta, but I still have an extra term KQ by R. So somehow this KQ by R needs to be removed. So for that we consider L is equal to 0 term. So if we consider L is equal to 0, P0 of cosine theta is simply 1. So you would have, for L is equal to 0, you would have A0 R to the power 0 P0 of cosine theta is equal to phi 0 of P1 cosine theta. So then we have KQ by R plus, I'm going to write this term first, A0 R to the power 0 is simply 1, P0 of cosine theta is 1, so I just have A0 plus A1 times R P1 of cosine theta is equal to phi 0 P1 of cosine theta. So you can see that this term and this term are matching. So these two terms, which are constant, should cancel out, or in other words, A0 should be equal to minus KQ by capital R. This is not the small r, right? And similarly, A1 of R should be equal to phi 0. A1 of R is equal to phi 0, or A1 is equal to phi 0 by R. Right? So we got the coefficients. A0 is equal to minus KQ by R. A1, these are all A's are all inside, right? A1 inside is equal to phi 0 by R, and we got B1 outside is equal to phi 0 times R squared. So then we can now write in general phi inside R theta phi, or just R theta in this case, because it's spherically symmetric, would be KQ by R coming from the point charge, plus we had a summation series, but we found that we have only two terms that come up from there. So A0, which is minus KQ by R, plus A1, that is phi 0 by R, times R to the power L, that is R to the power 1, times cosine theta. Similarly, this cosine theta comes from P1 of cosine theta, because this is L is equal to 1 term, and this is L is equal to 0 term, A0 and A1. Similarly, we can then write phi outside of R theta, that would be equal to just the B1 out term, so that is phi 0 R squared by R to the power L plus 1, so that is R square. We're writing for L is equal to 1 only here. Outside we don't have L is equal to 0 term because there is no charge outside the sphere in this example, right? And then times P1 of cosine theta, or that is equal to phi 0 R square by R square cosine theta. So outside in this example there is no L is equal to 0 term because there is no charge outside. For this term we have L is equal to 0 term as well because there is a point charge. So to balance that out at the boundary condition, we had to introduce this L is equal to 0 term. So in a very similar fashion, the problem we solved using image charges where we have plus q at a distance s from the origin, you can think about solving this by including the point charge in the outside potential rather than the inside potential, like how I have shown here. And then you will get an L is equal to 0 term in the outside potential and L is equal to 1 term only in the inside, and that's how it will change, right? And then you also have a little bit of offset in the current example that we did here. The charge is placed at the origin, but here the charge is not at origin. The charge is at a distance s, but that's just an offset. And so you could try to solve this problem with separation of variables. So this provides more insight into how we can use image charge. And as I mentioned, because this is more of an art than science, or as much art as science, you need more practice. And so I suggest solving homework 6 problems. The problems in homework 6 are given to you for practice. So don't think about whether these problems should be solved using separation of variables or image charge or some other method. Treat the problem as, in general, an electrostatics problem and see how you would like to go about it. You can use any method that you like. It doesn't matter. You don't have to solve that just because we try to solve a particular type of problem with separation of variables. You don't have to choose to solve that with that technique. You could solve it with, we discussed different techniques so far to solve for potential. So you can pick and choose any particular method that suits you and that you think suits the problem the best. So practice homework 6 more, and then we can discuss this more in the next Thursday session about homework 6 problems. Thank you.